Hi everyone. So today I'm just going to do a bit of a brief presentation on the analysis and management of non-credible risks in the Australian NEM power system with some additional information about Queensland islanding, which is one of the things we studied recently as a bit of a case study. So a bit about me, I'm Maddy. I've been working at AEMO for a bit under 4 years now. So I'm in the operations department. So previously I was in the grid performance integration team, which is the work that I'm talking about today to do the general power system risk review. But I've recently in the last few weeks moved to the operational analysis and engineering team, but that's also in the operations department. So in terms of what I'm going to cover in the webinar today, so as I said before, just a bit of background about the management of non-credible risks, what that sort of means, and how they're dealt with in the national electricity market, which AEMO operates. Then a bit of background on the general power system risk review, which AEMO publishes, and then a bit of background about some of the recent historical severe non-credible events that have impacted the Queensland to New South Wales interconnector, and then a bit of a case study on the studies that we completed looking at Q&I instability, the modelling approach, the results and observations, and then some of the recommendations that came out of that work. And as I go, feel free to pop questions in the chat, and I'll also pause to allow for some questions as well, and we should have time at the end for any questions, and I'm happy to take questions on notice as well if we don't get to them. So firstly, in terms of management of non-credible contingency events in the NEM, so this diagram is a very basic sort of overview of the NEM power system, in particular the sort of key AC interconnectors between the different regions. So if you're not familiar, obviously there's even though it's called the National Electricity Market, it does sort of only include the eastern states of Australia. So there's a separate power system called the WEM, which is obviously Western Australia, and there's a small isolated power system for the Northern Territory. AEMO also operates the WEM, but obviously separately, it's not physically connected to the NEM. So this diagram sort of shows the key 5 regions that make up the NEM, and then, the AC interconnectors between each region. And you also see that there's PEC, which is Project Energy Connect, which is a future AC interconnector from South Australia to New South Wales, which will be in addition to the existing AC interconnector Hailwood, which is from South Australia to Victoria. So the case study I'll be talking about today is focused on Queensland synchronous separation. So basically the tripping of this Q&I AC interconnector between Queensland and New South Wales. So you can see there's also a DC interconnector, which is actually called Direct Link. And then there's a small AC part of that circuit which connects to Queensland. But obviously if you lose Q&I, then Queensland loses synchronism with the rest of the NEM, and then you just have that DC interconnection remaining. So in terms of background about what we mean by credible versus non-credible contingency events. So the Australian Energy Market Operator, or AEMO, is responsible for maintaining power system security and reliability in the NEM. So when we talk about reliability, we mean the ability for demand to be met by generation or the reserve requirements. And then when we talk about security, we are talking about the ability of the power system to withstand a credible contingency and remain in a satisfactory state. So this diagram sort of shows, I guess, the transition between secure and satisfactory. So satisfactory just means that the power system is within its technical envelope or its normal operating bands and limits. So that relates to, frequency being within the required bands, voltage being within the required levels. Obviously, the power flows on the different transmission lines in terms of the thermal limitations of power system elements, fault levels, stability or oscillations in the power system, So all of those things have to be within their technical limits. And then in terms of what a credible contingency event means, that means an event that is considered to be reasonably possible. So that in the NEM usually relates to N-1 or the loss of single power system elements, because obviously that is usually reasonably possible. And so then when we're talking about non-credible contingency events, we mean anything else other than credible contingency events. So that could be the loss of multiple different power system elements simultaneously, or sort of cascading events that are lower probability but could have a far more significant impact on the power system. So in terms of, this diagram, you can see that AEMO basically operates the network in terms of how we dispatch generation and how we operate the system. We operate it to be able to withstand a credible contingency event and remain within its technical envelope or be satisfactory following that event. And then we also have an obligation to try and re-secure the power system following that credible contingency event within 30 minutes so that the power system is then secure again in case of, another credible contingency event occurring. In terms of non-credible contingency events, the only other thing I'd say is that, as I said before, credible events tend to be the loss of single elements, but AEMO can also reclassify non-credible events to be credible in the case of abnormal conditions. So that just means that if there's the most, frequent example is if there's lightning across certain double circuit lines, then the loss of both of those lines, even though it would usually be considered non-credible, can be reclassified as credible because it's sort of become reasonably possible based on the presence of lightning conditions in the area. So that means that then our operators can invoke the relevant constraints into NEMD to make sure that if, those two lines did trip simultaneously, we'd still land in this satisfactory sort of condition. We wouldn't become sort of unsatisfactory, and also we'd be able to re-secure for any following contingencies. So in terms of how we manage non-credible risks across the NEM and how AEMO and the TNSPs sort of try and mitigate either the likelihood or the consequence of these types of events. So firstly, there's sort of three key timeframes that you can sort of split up the management of non-credible risks. So obviously there's the operational timeframe, which is, as I said before, operators being able to reclassify a non-credible event if they think that it's more likely to occur. There's also what we call protected events, which is in the National Electricity Rules, which sort of relates to if AEMO believes that there is, a cost-effective way for managing a particular risk that it identifies, then the reliability panel can declare a particular contingency event as a protected event. So an example is SA separation was previously a protected event, but that was actually revoked. So currently there's no sort of protected events, and instead SA separation is managed under this reclassification framework. In terms of the planning time frame, the General Power System Risk Review, which I'll explain in the next few slides, sort of looks at different options for mitigating the consequence or reducing the likelihood of non-credible events. And then, as part of that, there could be recommendations for remedial action schemes or sort of protection schemes for the system that could, trip load, trip generation, or use batteries to discharge or charge to help reduce the consequence of a non-credible contingency event that occurs. And then obviously as well, following, a non-credible contingency event that's occurred on the network, AEMO also does, in conjunction with obviously the NSPs and any generators or participants, develops reviewable incident investigation reports, which are all published publicly. So they'll sort of go through all of the details around a particular event that's occurred. So for instance, there was an event on the 13th of February this year involving a tower failure, and Loyang generators tripping off. And so the AEMO incident investigation report will sort of go through the sequence of events, what caused the event, key findings, and also, again, sort of key recommendations for how to prevent a similar sort of contingency event from happening again. And this picture on the side here sort of lists some of the different abnormal conditions that operators sort of use as a reason to reclassify a particular event. So a lot of them do relate to weather, but some of them can be more, I guess, indistinct in terms of things like cyber attacks and that sort of thing. So you might reclassify a certain amount of generation being at risk. You might want to constrain down key interconnectors. If you're not sure exactly what particular element might be more likely to trip, you're just concerned that something generally bad might happen, and you want to, I guess, increase the security level of the network. So in terms of the General Power System Risk Review, which I've mentioned a few times, so this is an annual report published by AEMO. It's a requirement under the National Electricity Rules, or the NER. And so that requires AEMO to undertake a General Power System Risk Review at least annually. So that's 520A of the NER if you're interested to look at what the sort of legal obligations on AEMO are for that report. So this report sort of replaced the previous biannual Power System Frequency Risk Review, which was very similar, except the scope of that was mainly around cascading frequency events or contingency events, particularly impacting frequency, whereas the General Power System Risk Review sort of broadened that scope to include sort of anything, including obviously events directly impacting voltage stability, anything that could cause cascading failures or significant load disruptions. So listed here is sort of the key, I guess, things that we focus on when preparing each risk review. So firstly, selecting a priority set of risks or events or conditions that could lead to, as I said before, cascading outages or major supply disruptions, looking at what the current arrangements are for managing these sorts of events. So if there are any protection schemes, there are any emergency frequency control schemes, or any procedures in place like reclassification or anything like that to manage that particular event. And then looking at if, you know, different things can be developed to help reduce the likelihood or consequence. And also, lastly, looking at the existing emergency frequency control schemes or protection schemes and any need for modification of those. So in terms of how we select the priority risk events, this is sort of a collaborative process with the NSPs and also sort of industry in general. So as part of each risk review, which by the way is published publicly, similar to, you know, the ISP. So you can have a look at the risk review for each year on the AEMO website. And as part of selecting the priority risks, the NER also requires us to publish a approach paper which details how those risks were selected. So NSPs submit a risk assessment document sort of rating each risk in terms of likelihood and consequence. And then we sort of calibrate that to help select the priority risks for each year. And so that's all outlined in the approach paper, including how we propose to study it in terms of the methodology. And something we also want to consider is what, you know, in terms of this part, in terms of what future management arrangements we could put in place. And we also look, which you'll hear about in a few slides, we also look sort of 5 years into the future, because obviously if we're looking at a risk that is going to be alleviated by an augmentation in the next, you know, year to 2 years, there wouldn't be much point in recommending a protection scheme, for example, to mitigate that if that risk isn't going to be, you know, in the system, or the risk profile changes a lot within, you know, a couple of years. So yeah, generally we do sort of current system studies, but also studies looking 5 years into the future as well. So now I'll go into sort of an example of one of the things that we looked at in the 2023 risk review and also a bit in the 2022 PSFRR, which was prior to it becoming the General Power System Risk Review, which was looking at different non-credible events that could lead to instability on that Queensland to New South Wales AC interconnector. So in terms of recent events where the Queensland to New South Wales interconnector is tripped, one which was sort of the most recent significant event that occurred was the trip of multiple generators in central Queensland, which also resulted in a significant amount of under-frequency load shedding, and this occurred on the 25th of May 2021. And as I said before, because AEMO publishes detailed instant investigations, that report is publicly available on the AEMO website, and I believe like CS Energy has also published an incident report as well. So there's a lot of material on the event itself if you want to know more details about it. But basically, so the incident involved firstly Callide Power Station, which is a thermal coal power plant in central Queensland, which has two 350 megawatt generating units at Callide B and two additional 466 and 420 megawatt generating units at Callide C. And the instigating, I guess, part of the event was that the C4 generating unit boiler, turbine and field switch had tripped, but its generator circuit breaker had not tripped. So that left the generator motoring asynchronously on the power system. So it was absorbing approximately 50 megawatts and also 300 megavar from the power system. And this ultimately led to the tripping of multiple generators and transmission elements in Queensland following that initial event at Callide C. And this then led to under-frequency load shedding and also the QNI AC interconnection between Queensland and New South Wales tripping as well, which led to then synchronous separation of Queensland, and the minimum frequency in Queensland went down to 48.53 hertz. So that's below the UFLS threshold of 49 hertz. So this figure just shows the QNI flow during the incident. So as you can see, due to the loss of all of the different Queensland generating units, the QNI flow into Queensland rapidly increased, peaking at around 1,060 megawatts and then tripped. So usually before the QNI minor upgrade, I believe the import limit usually sits at around a maximum of 600 megawatts. And then, yeah, QNI tripped, but was then able to reclose around 16 seconds later. And yeah, the observed net power system load reduction was approximately 2,276 megawatts in Queensland and also 25 megawatts in New South Wales. So this event is sort of an example of how a severe generation loss within Queensland can lead to the QNI AC interconnector swinging above its import stability limit and then tripping to synchronously island Queensland. So as I mentioned before, as part of the 2023 General Power System Risk Review, we looked at different non-credible contingency events across the NEM that could lead to QNI instability for future operating conditions, so 5 years ahead, so looking at financial year 2027-28. And this followed on from a recommendation from the 2022 Power System Frequency Risk Review, based on observations that QNI could lose stability following different non-credible contingency events under both historical and future operating conditions. So in particular, studies showed that QNI could lose stability following the loss of the SA to Vic Haywood interconnector. So that's the existing AC interconnector between SA and Vic, causing synchronous separation of both SA and Queensland, with then potential further cascading outages. So yeah, I'll just go through this, I guess, as a bit of an example for how we'd go through assessing a non-credible risk and some of the things we might recommend as mitigating actions. So in terms of the different non-credible events across the NEM that we assessed as part of the 2022 PSFRR and 2023 GPSRR that could cause QNI instability. Firstly, we looked at, as I mentioned before, SA separation at Moorabool and Haywood. So obviously looking at SA separation for max SA export into Victoria and also import into SA. So that would be seen, I guess, as an effective remote load contingency for SA import and Queensland import scenarios, and then an effective generation contingency for SA export and Queensland export scenarios. And then we looked at a fault on the Loy Yang B Unit 2 transformer with a circuit breaker failure. So this particular CB fail event can result in the loss of both Loy Yang B units and also Valley Power. So that's just an example of a significant N-2 or CB fail event that can result in a significant amount of generation being lost south of Queensland. So obviously Loy Yang's in Victoria. So looking at a remote generation contingency event for Queensland export scenarios. And then lastly, I guess similar to the Callide event, we looked at a significant generation contingency, also including DPV shake-off in Queensland for Queensland import scenarios. So I'll just quickly run through the sort of modelling approach we used for the different studies. So in terms of the 2022 PSFRR, we used different historic PSSE cases that were taken from AEMO's OPDMS database for the period between 2019 and 2021. So this is sort of cases set up in PSSE, so in RMS studies based on actual historic dispatches, obviously looking at sort of boundary conditions for Q&I flow and contingency size and that sort of thing. So it's historical dispatches that sort of directly come from AEMO's EMS or energy management system and the state estimated results. So I guess it's based on actual historic dispatch conditions that we saw over those 2 years and looking at what the consequence would have been of these different contingencies for sort of the worst dispatch conditions across that period. Then we also looked at future operating conditions. So for future studies, we generally use market modelling data that's produced as part of AEMO's Integrated System Plan or ISP. So that allows us to pull out different likely dispatch conditions that take into account all of the constraints associated with, new augmentations and everything, and sort of works out what likely dispatch conditions there are. Obviously, it has all of the projected anticipated generation levels, DPV levels, demand levels, and also has all of the projected or anticipated generator retirements also modelled. So using that data, again, we pick out sort of the boundary condition dispatches that are likely to be the worst case for Q&I flow and the contingencies that we're studying. And so these studies were undertaken using a full PSSE NEM network model, which also included the relevant future augmentations, mainly PEC stage 2, which, as I said, is that future interconnector between SA and New South Wales. There we go. So in terms of the 2023 GPSRR studies, so again, we used PSSE or RMS, but we used a simplified model with grouped generation with generic models for each generator type. So in terms of having a generator and governor for, coal, gas, hydro, etc., and then generic models for wind and solar. And so the key advantage of this was being able to assess a wider range of future dispatch conditions and contingencies, with then using the full NEM PSSE model to benchmark the simplified model. We also included UFLS and DER models. There's separate reports on the AEMO DER models if you're interested, which is published publicly in terms of how they were benchmarked and developed based on and benchmarked against historical events and that sort of thing. In terms of load modelling, for the GPSRR studies that we did with a full OPDMS NEM model, we used the composite load model or CMLD, which represents sort of the different types of motor loads and sort of represents load shake-off and everything more accurately, and again has been benchmarked by AEMO for different historical events that has had load shake-off, and again that's in a report that's published if you're interested. But because, as it says on this slide, the simplified model can't accurately capture severe voltage disturbances, we only applied shallow faults in the simplified model. So therefore, it's not necessarily, I guess, to capture voltage-related load shake-off, as we're not sort of able to do that in the simplified model anyway. And in the NEM, which is a bit different to the WEM, I think, the frequency-dependent load relief is quite small. So I think it's at a less than 0.5%. And it's also projected to generally reduce into the future due to the general increase in inverter loads. So for the simplified model, we only used a ZIP static load model, just because, yeah, the frequency-related load relief is quite small. So it's probably, yeah, fine to disregard it for the simplified model. But yeah, for the full model, we did include it. We also modelled the Q&I distance protection. So this was to be able to model the tripping of Q&I in response to instability. And so, yeah, we just used generic PSSE models to model the protection relays for Q&I at Bully Creek and Doomarest based on data from PowerLink and TransGrid. And yes, because these studies were obviously for future operating conditions, we again included the PEC Stage 2 interconnector, as well as the remedial action scheme called the SATRAS, or the South Australia Interconnector Tripping Remedial Action Scheme. So this was also included in the 2022 PSFRR future studies. So this scheme is basically designed to help prevent SA islanding for following the loss of either Hayward or PEC. So basically trying to stop SA from islanding if you lose one of the interconnectors once PEC Stage 2 is commissioned. So basically trips load or generation, and it also signals best to charge or discharge depending if SA is importing or exporting to try and keep SA synchronized with the rest of the power system. So as I sort of touched on before, even though the simplified model can capture sort of frequency deviations fairly accurately, it does have a number of limitations. So firstly, it excludes obviously the actual network impedances, as lots of the network is lumped, so it can't accurately predict power system voltages. And so that then means that the model is only an approximation of the fault ride-through behaviour of IBR plants, and also of voltage tripping behaviour of DPB and also loads. And additionally, sort of power swings on interconnectors and their angular stability predictions may be less conservative compared to the full NEM model. And so to evaluate the accuracy of the simplified model we did benchmark it against the full NEM model, and also specifically tried to match the fault levels at key system nodes in the simplified model to see how accurately the model could predict Q&I instability. So we found that for the majority of the benchmarking cases, the simplified model showed instability on Q&I for the same contingency events where we saw instability in the full NEM model. So overall, we saw that the simplified model could capture Q&I instability, but couldn't necessarily predict the exact flow on Q&I at which instability occurred for a given contingency event. And this is consistent with what we observed in the 2022 PSFRR sort of benchmarking as well. But for the 2023 GPSRR future studies, the main, I guess, driver or aim of the studies was to investigate the different sorts of contingency events across the NEM that could cause Q&I instability, rather than to estimate the exact threshold at which Q&I would lose stability for a particular contingency event. So we were mainly looking at what the risk profile of this risk would be, and then what sort of remedial actions we can put in place. Whereas if you wanted to actually design the protection scheme, to prevent Q&I instability, you need to use a full NEM model to be able to accurately predict the threshold at which, you know, instability occurred for each sort of contingency event. So this diagram sort of just shows the structure of the simplified model, and then some of the sort of benchmarking results showing, you know, the instability. And so you can see the threshold at which instability occurs on Q&I is different, likely because, yeah, we can't represent the key system voltages, and the reactive power flows exactly the same. So then the transient stability results are going to be slightly different as well. So in terms of some of the results across the 2022 PSFRR and the 2023 GPSRR, for the historical operating conditions that we looked at for the 2022 PSFRR, we didn't see any issues for South Australia import cases where Queensland was also importing. However, we did see for export cases for both historical and future operating conditions that Q&I could become unstable following the separation of South Australia at Hayward or at Moorabool. So you can see here that for, I guess, the pre-contingent flow, so SA and Queensland are both exporting at fairly high levels, and following Hayward being tripped, Q&I sort of swings above its export stability limit and then goes unstable, and Queensland loses synchronism with the rest of the NEM. And then this future case obviously has PEC stage 2 included as well. So it involves SA separation at Moorabool, but obviously PEC stage 2 is still connected, and the SAT-RAS operates to trip generation to reduce SA export flow, but consequently was unable to prevent SA instability, and so Q&I and PEC both go unstable. So it's likely that both SA and Queensland would still island. Is there anything else on that one? I guess, yeah, for the future SA import cases in the 2022 PSFRR, it was still seen that load tripping from the SAT-RAS can still cause large power swings on Q&I. So we didn't see loss of synchronism, but we still saw large power swings on Q&I for the future import conditions. So in terms of the 2023 GPSRR results, so firstly, again, we looked at SA separation at Moorabool with PEC stage 2, and similarly, we did see instability for both export and import conditions this time. And we also included the Q&I minor upgrade. So we had Queensland export levels up to 1450 megawatts and import levels up to 950 megawatts into Queensland. And so for one import case where Queensland was importing 950 megawatts, SA lost angular stability with the rest of the NEM following separation at Moorabool and operation of the SAT-RAS, and the Q&I power flow then swung to approximately sort of 1400 megawatts import before tripping. And we also saw that the EAPT scheme operated as well, which separates the Moorabool area of SA. So yeah, we saw that, I guess, Moorabool separation with PEC stage 2 included has the potential to cause loss of stability on Q&I, which could then be exacerbated by existing remedial action schemes within Victoria and the SAT-RAS due to them tripping additional generation to try and prevent SA islanding. Also, a large amount of UFLS was tripped for a lot of the studies, so potentially more than 4,000 megawatts, which obviously results in a very severe load contingency event. Then in terms of the graphs that are shown here, so firstly, the graph at the bottom, which shows the loss of the Loy Yang B and Valley power units. So again, we looked at several different cases and we saw that the Q&I distance protection operated to trip Q&I for high Queensland export cases in response to the remote generation contingency. So for these cases, the Q&I export level was close to the maximum of 1450 and then swung to sort of around 1700 megawatts or a bit above, and then tripped off. And so the total contingency size of the generating units ranged from 580 megawatts to 1400 megawatts in terms of the amount of generation that tripped to cause that cascading failure. We also saw that for a lot of the daytime cases, a significant amount of DPV could also trip based on inverter settings due to the frequency falling below 49 hertz when UFLS starts to operate. So that as well sort of could increase the contingency size quite significantly in terms of the amount of generation that's tripped off. Then the figure on the top shows the Queensland generation contingency event for a Queensland import condition. So we found that for 4 of the cases we looked at, there was Queensland synchronous separation following the loss of Millmerran units as well as DPV shake-off in Queensland. So we saw that the Q&I flow swung up to around 1400 megawatts before tripping. And for this particular case, you can see that there was also insufficient UFLS in Queensland to prevent Queensland frequency from collapsing below 47 hertz. So again, this also highlights the importance of UFLS and the need to ensure adequate UFLS to prevent system collapse following major contingency events. So following on from this, we did also complete some sensitivity studies looking at tripping load in Queensland or New South Wales following fault clearance to try and prevent Queensland from losing synchronism with the rest of the NEM and Q&I from exceeding its stability limits. So the sensitivities confirmed that tripping load in New South Wales or Queensland through the action of a remedial action scheme or protection scheme could prevent Q&I from losing stability and Queensland from separating from the rest of the NEM. I think, yeah, so in terms of conclusions and next steps, so I guess, yeah, this non-credible risk was considered as a bit of a case study to show how we look at different non-credible contingency events as part of the general power system risk review, and the sort of things that we consider. In terms of the recommendations around Q&I instability, so the relevant NSPs, obviously Transgrid and PowerLink and AEMO, are looking into the feasibility of a remedial action scheme to try and prevent Q&I instability for different remote contingency events. And also, yeah, I guess it also highlighted that other protection schemes like the SATRAS, like EAPT, can impact interconnector stability across the NEM based on tripping, sort of additional generation and load. And also, as I mentioned before, there's already an outstanding recommendation from the 2022 PSFRA for remedial actions to be taken to restore Queensland UFLS load to ensure that there's sufficient UFLS to operate if Queensland does island to prevent frequency from collapsing. And there's some links there as well if anyone wants to read up on anything else. Does anyone have any questions on anything I covered? As I said before, yeah, a lot of the links sort of have detailed reports on anything.
There are 2 questions in the section. Would I read it out for you if you want?
Yeah,
sure. Now, first of all, thanks for the great presentation. Looks a lot of work you put out on the analysis, the risk management. So thanks for that. Reading on the first question, Pat is asking, what are your reflections on AEMO's ability to predict, assess, and simulate future possible non-credible scenarios? And where could improvements be made to improve the current GPSRR assessment process?
Thanks, Pat. who also works at AEMO. Yeah, I think part of, I guess, the difficulty of trying to remediate non-credible events is that, firstly, yeah, it's difficult to predict, obviously, the cascading failures that can happen for these sort of severe events. So even using the 13th of February event as an example, I don't think anyone would have predicted that a tower failure into SA would then cause, the Loy Yang power systems the Loy Yang generators to trip off as a sort of cascading failure. So I guess that's one thing that's also difficult. And then the other thing that's also difficult is when we're looking at recommendations or what we should do to mitigate the consequence. Again, because these events are less likely, but definitely higher impact, it's hard to also calculate the risk cost assessment or work out how much money we should spend on mitigating this risk, given that it's might be really low probability, but it could be really high consequence or cause a blackout. So those are sort of two of the main things that is quite difficult. I would say in the last risk review, we did try and I guess highlight, the possible unexpected cascading failures like additional loss of generation. So we try and build a lot of, I guess, fat into what we recommend. So for instance, for the UFLS screening studies that we did looking at UFLS adequacy, we trip off lots of different combinations of stations to try and work out what the, I guess, worst case would be or what the requirement is in terms of how much we should protect for. But yeah, in terms of improving analysis of non-credible events, I think the incident investigations are really good in terms of tying that into the risk review and making recommendations based on actual events that have happened. But I think the key thing is having accurate power system models, having accurate information from generators, accurate protection settings, because of a lot of unexpected cascading failures end up being due to unexpected protection operations or settings we didn't know were there, or settings that were wrong. So things that we didn't know were there, and then of course we can't simulate them because we don't have that information in our models. So I think that's probably the key thing we can do to improve our analysis, is having as much accurate information as possible from both generators and NSPs to really understand how the network would behave for these different events, to then try and predict these different things. Because if we don't have accurate models, then we don't have any hope, I guess, of anticipating any of these sorts of things.
Awesome. Second question is Ronan asking, as IBR penetration increases, how much inaccuracy does approximating fault right through, etc., introduce to the GPS RR future simplified model? And how can this be addressed if need be, given that the penetration schemes of IBRs are often black boxes to power system operators?
Yeah, so I definitely say so. For instance, for the 2024 GPSRR, we looked at the non-credible loss of HumeLink, which is like a future double circuit in New South Wales. So for those future studies, we used a full NEM model. And again, that was because we were looking at sort of voltage collapse and things like that. So we weren't able to use a simplified model anyway. I would say that for increasing IBR penetration, I guess, yeah, it depends what you're looking at. Like, the shortcoming of this model is that any sort of DPV shake-off or IBR fault ride-through issues that then result in a frequency disturbance or a loss of generation we can't simulate. We did include like certain percentages of DPV shake-off based on what we thought was reasonable, based on sort of real events and studies in the full model. But yeah, for anything regarding like voltage, fault ride through of generators or DPV, you really have to use a full model, which is why we often do for different, future studies. I'd say as well, obviously, it's important to use EMT or PSCAD for anything where you're looking at sort of unbalanced faults or sort of oscillation events where you need a shorter time step, where it's not linearized. But the issue with that is you can't look very far into the future, I guess, because you need accurate system models, as you said, that are black boxed, that are representative of the actual plant. So usually we only do EMT studies looking up to 2 years ahead. But yeah, that's all sort of consideration when we look at what risk we're looking at, what we're trying to simulate, whether it's frequency or something else. And yeah, there's lots of assumptions in terms of what we're not able to capture and therefore what we are or aren't able to conclude from the study results.
Okay. Next question, Akshay is asking, how far in advance does AEMO complete the studies? Does it include potential future assets such as synchronous condensers being in service?
Yeah, so that's a good question. So as I said before, all our future study conditions are based on assumptions from the most likely scenario from the ISP. So if you want to understand a bit more about how the market modeling stuff works in terms of how they come up with that, there's lots of documentation on, you know, how they develop that for the ISP. But that includes sort of how much generation and load and retirements are there. I don't think it includes really system security stuff. And we also don't enforce the system strength constraints in the future modelling. So that's, I guess, something we have to be mindful of in terms of what realistically we'd expect the system strength to get down to and be remediated to. But yeah, certainly we also include any like network augmentations that are part of the ISP constraints. So like, you know, PEC, HumeLink, and then any network assets associated that. So for instance, PEC has syncons associated with it. So we include, you know, depending on how far away it is, whether we can include site-specific models or generic models. Yeah, we'll definitely include those in our dynamic studies.
Okay. There is another question from Sylvester is, was the prediction done by training a machine learning model and testing with unseen historical data for the prediction accuracy?
So in terms of machine modeling data, I mean, at the moment, we're not using anything like that. It's more looking at trend analysis and picking out sort of the boundary conditions in terms of what we think is a worst case for the contingencies we're looking at. And that's how we'll pick which historical dispatch conditions we'll study. So obviously looking at the ones that have the sort of largest contingency size or the worst network flow cases, or, you know, if it's a system strength issue, then picking the ones with least synchronous units online. So yeah, that's sort of how we pick which conditions to study. I don't know if that answered the question.
I hope it answers well. We'll move forward with limited time and lots of questions. Walter is asking, just wanted to ask to extend where network impedance is simplified in the model. Just curious if there were any concerns about the distance protection operating in model versus how it would actually respond to network disturbance.
Yeah, so the interconnectors were modeled as per the full system model, but certainly, certainly the transient stability is slightly different, and also probably the distance protection. But yeah, the interconnector impedances and everything were the same. So yeah, it was definitely an approximation, but it was good enough, I guess, to see Q&I instability for different events. But yeah, we often now use a full model if we're looking at exactly like when protection would operate or not.
Awesome. Ines is asking, how would AEMO assess the likelihood versus consequences of each non-credible contingency? How would different system recovery or planning consider the statistical possibility of events? And
Yeah, so, oh yeah, you
sorry, follow-up question is there as well. To what extent would protection upgrades or improvements change any response to events?
Yeah, so this is part of, I guess, as I said at the start, how we select the priority risk events that we'll study each year. So as part of the risk assessment that NSPs will submit, they'll raise like a particular contingency event in their network or a particular risk, and then they'll rate it in terms of likelihood and consequence, including if it's, actually occurred historically at any time, and that's like rated out of a certain score, and then there's like a total score that takes into account likelihood and consequence. And you can, the approach paper has a bit more on how like likelihood and consequence are defined. But broadly, I guess, it's looking at events that can lead to severe cascading failures and load disruption. So I guess, only events that would cause like a region to island or a significant amount of load to trip off are sort of deemed severe enough for us to look at. In terms of protection and stuff, so again, as part of that risk assessment, they'll list any relevant protection schemes that are currently in place or that are planned that relate to that particular contingency event, and we'll sort of get that data again from them if we, go ahead with studying that particular risk. So definitely all that information is included in terms of how we study the risk or what we'd recommend as well. Yeah.
Awesome. Second question from Sylvester was that as per plot on the Kelite event, did the QNI interconnector close 10 seconds later because the Kelite power plant in monitoring mode tripped within this period?
Yes, so QNI, I believe, reclosed within about 16 seconds. So Queensland was only islanded for a short period of time, which was good.
Awesome. And there is another question from Andrew is once an issue has been identified, how long before a solution has to be developed and implemented under the current rules?
Yeah, so this is a good question. I mean, there isn't a set time frame, I guess, because it's quite broad in terms of what we could recommend. I'd say in terms of like a system protection scheme or something like that, we'd ideally like that to be implemented within under 5 years. I guess that's why we tend to look 5 years ahead, is that a lot of remediations take time to put in place. So there's no point, I guess, trying to remediate something that isn't there in a couple of years due to an augmentation or something. But there's no strict requirements for networks to implement something within a specific time for non-credible contingency events. I would say that in terms of planning, there is clause S518 that does require NSPs to consider non-credible risks that could lead to cascading failures across the NEM as part of their planning process. So that usually means that for like new big augmentations, NSPs already have to start thinking about if they need a system protection scheme or something in place, be it surge arresters or something to try and reduce the likelihood. They already have to sort of think about that when they're planning their network as well. But in terms of timeframes, there's no strict timeframes on it. It's mainly about, when they can implement whatever we've recommended.
Thank you. And I think that's all the questions we had. You addressed every question satisfactorily. And again, thank you for the presentation. It was very enlightening, at least for me.
No worries. And if anyone has any questions, feel free to email me, or else, there's lots of published stuff. So feel free to have a look at the incident investigations or the risk review if you want any more information.
All right. Thank you then. We are well below the timings. And thanks again, Maddy from NGN Australia and every participants. And thanks everyone for joining with us today. So have a great weekend and see you in August with another essential webinar. So
awesome. Thank you.
see you.
Hey, everyone.
Thanks. Bye.